The first law of thermodynamics. In previous sections of this chapter, we defined internal energy, heat, and work in thermodynamics. Now we will combine them into one formula, expressing conservation of energy in thermal processes. We have learned that there are two ways to increase the internal energy of a thermodynamic system. Either you add heat to the system, or you do work on the system. The first law of thermodynamics, a change in internal energy equals heat plus work. We will next look at the four different types of thermodynamic processes and their effect on the internal energy of a thermodynamic system. Each process takes place in a situation where a particular thermodynamic quantity is fixed. We have seen three of these previously, but one is new. Isothermal means constant temperature. The change in T equals 0. Isobaric means constant pressure. P is constant. Isovolumetric means constant volume. Delta V equals 0. And a new one, adiabatic, means no heat was added or removed. Q equals 0. In an isothermal process, the temperature is constant. Here we see a PV diagram with an isothermal process, and you can see that nice gentle curve. For an ideal gas, since the internal energy U depends on T, the internal energy is constant, which means delta U equals 0. Since we have the first law of thermodynamics, and delta U is 0, that means that Q must equal negative W. All heat added to the system is converted to work by the system. In physics, isothermal processes will generally involve very slow expansions and contractions. Clues that give away that it is an isothermal process include at a constant temperature, the involvement of a hot or cold reservoir, and the words very slowly. An isotherm is an isothermal process. So here is the graph of an isotherm. Some real-life examples of isothermal processes include phase changes. Earlier, we learned that the term phase refers to a specific state of matter, such as solid, liquid, or gas. When a substance undergoes a change from one state to another, it is called a phase transition. Phase transitions at a given pressure take place at a constant temperature, are accompanied by the addition or removal of heat, and may involve a change in volume and density. Examples include water freezing, water vaporizing, ice melting, and steam condensing. We will focus on phase transitions in water. Ice melts at 0 degrees Celsius. For 1 kilogram of 0 degree ice to change completely to water at 0 degrees requires the addition of 334 kilojoules of heat. Similarly, to freeze 1 kilogram of 0 degree water into 0 degree ice requires the removal of 334 kilojoules of heat. The heat added to change a solid to liquid or removed to change a liquid to a solid is called the latent heat of fusion, L sub F. For water, L sub F is 334 kilojoules per kilogram. Water vaporizes or boils at 100 degrees Celsius. For 1 kilogram of 100 degrees Celsius water to change completely into steam at 100 degrees Celsius requires the addition of 2260 kilojoules of heat. Similarly, to condense 1 kilogram of 100 degree steam into 100 degrees Celsius water requires the removal of 2,260 kilojoules of heat. The heat added to change a liquid to gas or removed to change a gas to a liquid is called the latent heat of vaporization, L sub V. For water, L sub V is 2,260 kilojoules per kilogram. Phase transitions of water. Here we have temperature versus heat. Water transforms from ice to liquid water to gas or steam as heat is added. During phase transitions, so this part here and this piece here, the graph is horizontal, meaning the temperature stays constant while heat is still being added. While in a single phase, ice or water or steam, the temperature rises as heat is added. Notice that when a phase transition is taking place, the temperature remains constant. Where is the energy going to or coming from? The answer is that it is going into making or breaking bonds between the atoms or molecules of the material. For instance, when ice melts, the bonds that hold the water molecules in place are broken with the addition of energy. When that energy is removed from water at 0 degrees Celsius, the molecules bond again, crystallizing into ice. In an isobaric process, the pressure is constant, giving us this horizontal line on a PV diagram. Since work equals negative P times delta V, work is done as soon as the volume changes, and the volume is changing at a constant pressure, therefore work is done. And temperature is allowed to change, therefore the internal energy is going to change as well. So you can use the first law of thermodynamics to solve problems. Heat added to the system causes the system to do work, and it will also increase the internal energy. Clues that give away that it is an isobaric process, just the quote, at a constant pressure. In an isovolumetric process, the volume is constant, giving us a vertical line on the PV diagram. This means that pressure and temperature, and therefore internal energy, change. Well, since work equals pressure times change in volume, since there is no change in volume, there's no work done. Therefore, we have our change in U equals Q plus W equation. There's no work. Therefore, the change in internal energy is the heat added. So heat added to the system increases the system's internal energy. Clues that give away that you're dealing with an isovolumetric process include at a constant volume, the quote, the piston is locked, and the involvement of a rigid container. In an adiabatic process, no heat enters or leaves the system, so Q equals 0. Since Q equals 0, any work done on the system increases its internal energy, because remember we have change in internal energy is Q plus W. Since this is 0, that means that the change in internal energy equals the work. Any work done by the system will decrease the internal energy. And you can see the graph of an adiabatic process is a curve, but it's steeper than an isothermal curve. So here we're going from one isotherm to a different isotherm. That's an adiabatic process. So it's not as gentle as the isothermal curve. It's steeper. Some examples of adiabatic processes include explosions, implosions, and highly insulated processes. Clues that give away that you are dealing with an adiabatic process include highly insulated, no heat transfer, or very quickly. On a PV diagram, you can see a jump from one isotherm to another. The graph looks similar to 1 over x, but it is steeper. So here we have an isotherm, and there we have an adiabatic curve. Here we have a summary of the 4 processes, their specific conditions, and how the first law of thermodynamics can be applied to each of them.